Let's have a bit more of a look at combinatorial logic and how we use Boolean algebra within combinatorial logic. Essentially, circuits are made up of combinations of different logic gates, and at any time we know that the expression of the output is dependent on the expression of all the inputs to that logical circuit. And it's really crucial for us to know what all those inputs are to generate a particular output. Now, there's two common ways that we write our circuits down. We've got our sum of products form that we'll look at first, and then we've got our product of sum forms. But essentially, our sum of product forms, we have two or more AND terms that we OR together. So it looks like this. We have three AND terms in this case, and we OR each of those ones together to give us our final expression. And essentially, this means that any one of these terms, which we call min terms, if any one of those terms is a high, that will switch the output or the Z value to a high, because this feeds into an OR. So any one of these needs to be a high, and that makes the output a high. Conversely, we can go the opposite way. So we can have a product of sums where we have a number of OR terms that we've got in our brackets here, and we AND them all together. And what we find in this case is if any one of these OR terms generates a low, our output, because we're feeding it into an AND gate, is going to be 0. It's going to be a low as well. Now, one of the reasons why these sort of things are important is if we're trying to go directly from a truth table, like we've got here, to a circuit, we can read these off and convert them to these min terms directly. So we can see in this case that if we look down our Z column, we've got two cases where our Z equals 1. And by inspection, we can read off that the first case, A needs to be 0, B needs to be 0, C needs to be 1, and D needs to be 1. And our second case, A needs to be 1, B needs to be 0, C needs to be 1, D needs to be 1. We can see those directly. So they're there two times when our Z's high. Now we can very quickly create a Boolean expression and a circuit that corresponds to each of those. So our first one, the Boolean expression for that one, Z's equal to A bar, B bar, C, and D bar. And we have our relevant circuit to that. And the other one, Z's equal to A, B bar, C, and D, and a relevant circuit to that. Now, in our sum of products form, we say we just join those two together, we OR them together, and that gives us our final expression Z. So it becomes very, very easy to go straight from a truth table through to a final circuit.